All right, welcome everybody to day 2 of the workshop on federated learning and analytics. We're so excited to have you today as well. Yesterday was a great success. As you can see on this slide, we have a very interesting schedule for today. We're going to start in a bit with Professor Virginia Smith in our second keynote, and then at 10 a.m. We're going to have a set of talks from Brendan, Mehriar, and Françoise from Google. And then at 11 a.m., we're going to have our 2 tracks of lightning talks and interesting discussions between a number of academics and Googlers. And finally, at 12, we're going to continue the breakout discussion sessions we started yesterday, and then have closing remarks. Just a reminder, tomorrow we have the workshop on TensorFlow Federated. It's going to be live streamed on YouTube. We strongly encourage you or your students to watch these nice tutorials if you want to learn more about TensorFlow Federated. These are the lightning talks for today. We have 2 tracks like yesterday. Track 2, which is on privacy and security, is not going to happen in this room. Please check the website for the Google Meet link. As a reminder, we have additional recordings that we could not cater and feature in this workshop, but they are on our website, so please watch them when you have time. And on this note, I want to remind everybody that we're doing all our discussions and Q&A over Dory, so please watch Dory. You'll not get notified when somebody pins a question, so you have to go there and refresh, but please engage in conversations and discussions over Dory. Today, we are going to have 6 instead of 8 breakout discussion sessions. You can see that scaling and IoT have been combined together because a lot of the discussions were pretty similar. And the differential privacy and secure computation sessions were also combined together. So we end up with 6. Please check our websites for the updated Google Meet links to know which session to join. And now we're ready to jump into our keynote. We have Professor Virginia Smith. Professor Smith is a professor at CMU in the Department of Machine Learning. She has done a lot of great work on optimization, machine learning, and especially federated learning. She's been exploring this space for the last couple of years with a lot of great papers. Yesterday in Vitali's talk, Vitali emphasized tail accuracy and local adaptation as a way to improve tail accuracy. Today, Virginia is going to take a different spin and tell us about how we can do it during optimization by tweaking the loss function. So Virginia, please take it away.
Awesome, thanks, Peter. Yeah, and thank you all for being here. I know it's a little early on the West Coast, but yeah, I'm grateful for the opportunity to speak. And can everyone hear me okay, by the way?
Yes, we can.
Okay, perfect. So I'm gonna go ahead and share my screen, and then I might turn my video off just for the presentation, and then I'll pop it back on when we do the Q&A. Okay, so can you see my screen okay? Yes, I'm seeing a thumbs up. Great. Okay. If there are any issues with the slides, just stop me, please. But yeah, so thanks, Peter, for the introduction. So my name is Virginia Smith. I'm an assistant professor at Carnegie Mellon University, and today I'll be talking about some work that looks at various ways that heterogeneity affects the federated learning pipeline. The works I'll be talking about today are joint works with a bunch of just fantastic collaborators, students, and researchers. So I'll be highlighting those individuals throughout the talk. So given that this is a workshop on federated learning, I'm not going to do too much to motivate or explain the problem of federated learning, but just so that we're all on the same page. A lot of the work I'll be talking about today deals with the cross-device setting of federated learning. So the goal at a high level will be to fit a model to some data that's distributed across a network of potentially hundreds of thousands to millions of devices. And in particular, the way that we'll think about fitting this model is by solving this ERM type objective. So we want to minimize an objective of a sum of losses over our devices. So F sub k will represent the loss on device k. So what makes this setting really unique and interesting is I think that there are a lot of challenges that slightly differentiate it from previous work. So one is that issues like communication can be really exacerbated in this setting. The network can be massive, it can be slow and unreliable. There are also, as we talked a lot about yesterday, I think terrific privacy concerns in this setting. So these can stem from user privacy constraints or legal or ethical issues with sharing data. But one thing I want to highlight in particular that really differentiates federated learning from traditional distributed computing in the data center setting is the issue of statistical heterogeneity. So whereas in a data center, you might assume that the central server has access or kind of owns all of the data and can move where that data belongs across worker machines. Here, the data is coming to you as is. So the data can be really unbalanced across devices in the network, and it can be really non-identically distributed. So some devices might contain data that looks very different than the data on other devices. And this heterogeneity plays a role not only in terms of the data, but also in terms of the underlying hardware. So the devices in the network might have diverse hardware or connectivity or power, and all of those issues can change how those devices are able to participate in this training procedure. So I just wanted to mention very briefly that we talk about a lot of these challenges and some future directions in this recent survey paper. And this survey paper is really meant to be kind of a very abridged version of the high-level research problems in this direction. But if you're interested in talking more about some of these challenges, I think this survey is potentially a nice resource. I think all of these challenges are extremely important, and they're important to think about in a holistic way if we're going to be able to truly solve the problem of federated learning. But for this talk, I'm going to focus specifically on these issues of heterogeneity. And there are a few questions that we're going to look at today. And the questions relate to how heterogeneity affects federated learning. I think one of the first questions, and potentially the most obvious question, is how does heterogeneity affect the optimization procedure? How does it affect the convergence of methods that we know? And can we develop new methods that are robust to the issues of heterogeneity? But the issue of heterogeneity doesn't just stop with the training procedure. So we're also going to talk about how to evaluate the model that's been learned across diverse networks, and in particular, to think about ways that we can potentially equalize the performance of that model across tail data, so across these very heterogeneous networks of devices. And finally, I think it's important to note, and this kind of mirrors the keynote from yesterday, that there are certain scenarios where when you have data that's so heterogeneous, it might not make sense to fit just a single global model to your data. So we'll also talk a little bit about the role of personalization in solving some of the problems having to do with heterogeneity in federated learning. So roughly these kind of major questions bucket into talking about optimization, fairness, and modeling. And we'll touch on each of these in the talk today. So first, let's talk a little bit about optimization and heterogeneity. Oops. Sorry. Can you guys still see my screen? Hopefully. Okay, so just as a refresher, one of the most common methods for optimization in the federated setting is federated averaging. The way that that works at a high level, as we all know, is there's a central server who's often coordinating this process, and at each round, that coordinator sends the current model update to a subset of the devices. Those devices then perform some local training. So for example, they run e-epochs of stochastic gradient descent locally, and then they send back their model updates, which are then aggregated, in this case averaged, at the central server. So this method is really nice because it's very simple, and even though it's a heuristic, it works remarkably well in practice for a lot of problems. But I think an important thing to remember is that it can also diverge, and we'll talk about that in just a moment. It can, the convergence behavior can really start to degrade, particularly when we're dealing with heterogeneous data. Okay, so what exactly do I mean by that? If you look at the performance of federated averaging on some data that has some statistical heterogeneity, this is an example with the Shakespeare data set, and you look at the convergence behavior of federated averaging. So here we're looking at the number of communication rounds on the x-axis, and on the y-axis, the training loss. So what you see is that if you set the number of local epochs to be relatively small, you can have this reasonable convergence behavior. So you're able to, reduce the training loss over time. However, as you start to do more work locally, you can see this behavior that you start to, converge in a much worse way. So you can either have this really unstable convergence, or you can potentially diverge. Okay, so the key takeaway here, I think, is that in this heterogeneous setting, doing too much local work can really hurt the convergence of these optimization methods when we're dealing with heterogeneous data. And by the way, most of the plots I'll be showing in this section show training loss on the y-axis, but the same trends hold in terms of test accuracy as well. So you can see test accuracy here on the right. We're actually converging to a worse solution in terms of the final model. So this is an issue not just with statistical heterogeneity, but it can become a real issue when you also incorporate the concerns with systems heterogeneity. And what I mean by that is if you take a data set and you look at this training curve, and you assume that all of the devices are participating and there are no issues with stragglers, or with certain devices having variable hardware or connectivity, that would mean that those devices are not able to fully complete some number of epochs within a communication time window. There's still some jitteriness from the statistical heterogeneity, but if you additionally add the issue of systems heterogeneity, this can really tank the performance of these optimization methods. And what's going on in this experiment in particular is we're looking at the scenario where there might be a high level of systems heterogeneity, such that you go out and you ask a subset of the devices to perform some number of epochs of SGD locally, and then you only hear back from 10% of those devices. And this is a really common strategy in dealing with heterogeneity from the system side, is that we can just drop devices that are straggling at a given communication round. And what we're highlighting in this plot is that this can really exacerbate issues that already exist because of the statistical heterogeneity in these settings. Okay, so how can we deal with these two sources of heterogeneity? In prior work, we developed this framework called FedProx to handle heterogeneity in federated settings. And it makes a pretty straightforward modification to federated averaging. So the idea is that the source of difficulty with this heterogeneity is that we're going too far and we're doing too much local work, and it's kind of pulling us to these local optima on the various heterogeneous devices instead of the global optima. So one way to handle that is just to prevent too much local work from happening. And that's what is going on with this proximal term. So basically, we're solving for some model update W sub k, but we're not allowing that update W sub k on device k to stray too much from the previous global iterate WT. Right, so this proximal term is limiting the impact of heterogeneous local updates. And this is particularly useful when you have also the issue of systems heterogeneity, because what we do in FedProx as well is rather than just dropping devices that aren't able to complete their local training in a given time window, we allow all of that partial information to be sent. So we allow devices to perform a variable amount of local work, and then we safely incorporate that variable work by adding this proximal term, which leads to more well-behaved updates. So this is a generalization of federated averaging. One way I think it's actually quite general is that our analyses are just in terms of this local subproblem, and in terms of performing a variable amount of work with respect to this subproblem. So you can actually use any local solver. You could use SGD, you could also use a momentum method or a second order method, and our analysis would cover that scenario. Okay, the other nice thing about this proximal term related to the analyses is that it makes it slightly easier because it allows for these well-behaved updates to reason about the convergence behavior of this method. So let's talk at a high level about the convergence guarantees. And I'm not going to say too much because there's been a lot of terrific work since this work came out, kind of tightening these rates and understanding them under slightly different settings. But I think a lot of the key ingredients here show up in other works as well. So I wanted to highlight a few of the main parts of the convergence proof. In particular, one of the high-level things to note is that we're looking at the convergence behavior of FedProx under a large number of challenges. So we're assuming that the data is non-IID. We're assuming that you're doing local updating. We're allowing for partial participation amongst the devices. And even more than that, we're allowing for the devices that participate to perform a variable amount of local work. So this is a really challenging setting to try to understand the convergence behavior of this method. Additionally, in order to understand the effect of statistical heterogeneity on this method, we make the following assumption. So we understand how much variability there is in the network via this dissimilarity assumption. And this assumption has been used in previous contexts as well. So for example, this has been also referred to as gradient diversity, which has been used to look at kind of scaling up mini-batch methods in the distributed setting. Here, the notion is a little bit different in that this dissimilarity idea is a bad thing in the sense that the more dissimilarity, the more diversity we have, the slower our convergence becomes in the federated setting. And you can see that in terms of our convergence rate as well. So the rate itself here is not super spectacular. Again, this has been kind of improved in follow-up work. But the key thing to note here is that we're able to show that the method converges despite all of these difficult challenges, despite covering non-convex losses, non-IID data, local updating, and partial participation. And the big thing in terms of the convergence rate is that the following relationship holds. So the more dissimilarity there is in the network, the larger you'll have to set this mu parameter, which will then slow down your convergence rate. So I think that's intuitive. The more heterogeneity there is, the more we're going to be limiting those local updates that can kind of make you stray too far away from the global optima, and the slower your convergence rate will become. Okay, so let's look a little bit about how this performs empirically. So if we forget about for a second the issue of systems heterogeneity, even with just fixed statistical heterogeneity, what FedProx can allow you to do is by having this proximal term, you can improve the convergence behavior of a method like federated averaging. So including this proximal term can help to lead to more stable convergence with statistical heterogeneity. When you add in the problem of systems heterogeneity, so for example, that there are a large number of stragglers at every round, the first thing to note is just that instead of dropping those devices, but instead incorporating some partial work from those devices, you can really help to improve the convergence behavior, and things become even more stable on top of that when you have this proximal term. Okay, so these two ingredients help when you have kind of both the issues of systems and statistical heterogeneity, which can happen a lot in practice because of the variability coming from both of these aspects of federated learning. Okay, just as kind of a takeaway from these results for all of the data sets that we looked at, so we looked at 5 data sets from the LEAF benchmark for federated learning. And when we have both systems heterogeneity and statistical heterogeneity by using FedProx, we're able to get a 22% absolute test accuracy improvement on average. So this is not only making training more stable, it's also improving the final model that we arrive at via training. So we're able to improve the absolute test accuracy. Okay, so going back to this question of how does heterogeneity affect optimization, I think there are a few really clear takeaways. So one is that heterogeneity can lead to slower convergence, reduced stability, and even divergence. And given that this is true, and I think that this is evident in a lot of the more recent work looking at heterogeneity and optimization, it's really critical to understand and evaluate and analyze federated optimization under these realistic constraints, under the assumption that the data is non-identically distributed, that there might be partial participation, or even that the devices might be performing variable amounts of local work. Okay. Now the issue with heterogeneity doesn't just stop again with training. And in particular, one issue with kind of just using vanilla empirical risk minimization for federated learning is the following, which is that the goal in ERM is to minimize the average loss across your network. So each of these losses here correspond to the loss on a single device. And if all we care about is the average performance, there's no real accuracy guarantees for individual devices. And I think that this was, highlighted in the keynote yesterday as well. There needs to be some incentive for these devices to want to participate in the federated learning procedure. So we really want to prevent against there being catastrophic failures on some of the devices. Okay, and in particular, if we're doing well on average, we might be doing well in terms of this one statistic, but at the cost of the performance varying widely across the network. So just to give you one example, this is from a real federated data set. I think this is the vehicle data set. What you can see is if we look at the test accuracy distribution of solving this ERM problem, and here this is a histogram just showing the test accuracies for various devices. What you can see is that, well, we're able to do well on average via this ERM objective. It might be at the cost of the accuracy on a few of these devices, right? So this is sort of this catastrophic failure example. So we're doing well on average, but a few of the devices have very, very poor performance. Okay, so the question that we asked ourselves in this work is, can we still try to do well on average, but can we encourage a more fair or uniform distribution of the model performance across the network? And the way that we thought about tackling this problem, we actually drew some inspiration from a slightly different community, which is that we're looking at a notion of fairness from the wireless sensor networks community. And there, fairness is often defined as having some resource that you want to be able to share across the network. So for example, communication bandwidth, and you want to share that resource in a fair manner. And to draw an analogy to federated learning, the way that we thought about the resource in this setting is that the resource for federated learning could be these losses. In particular, if one of the devices has a very, very large loss, and you're trying to minimize the average loss, the model is naturally going to overfit to that data that has a very high loss value. Okay, so we kind of drew inspiration from this prior notion of alpha fairness, which is used kind of not in the machine learning literature, but that allowed us to arrive at the following objective, which is a variant of empirical risk minimization, where basically what we do is we take the losses and then we raise them to this exponent, q+1. So at a high level, what this is doing is that if you had a loss that was, large before, now the loss is becoming exponentially larger. Okay, and in the extreme, this can recover some prior notions of fairness that have been looked at. So for example, if Q approaches 0, we're recovering traditional ERM. If Q approaches infinity, what we're going to be doing is minimizing the performance on minimizing the worst performing loss. So this is a notion known as minimax fairness. It's been explored both in the fairness literature and in the federated learning literature. So in the fairness literature, this is often called representation disparity. In federated learning, this has been looked at through, for example, agnostic federated learning. Okay, what's nice about this framework, which we're calling QFFL, so that stands for Q Fair Federated Learning. So Q Fair is similar to alpha fairness. What's nice is that you can tune it depending on how much you care about accuracy versus fairness, whether you care about this most extreme notion of minimax fairness or whether you care about something between these two extremes. And what we show in this work is empirically, we show the effect of using this framework on real federated data sets, and we show some intuitive theoretical results, which is that increasing the value of Q results in more uniform accuracy distributions, both in terms of the training accuracy and the test accuracy. So let's go back to the previous example from before. So the baseline of traditional empirical risk minimization, again, it can do well on average, but you might have these examples where the model is performing quite poorly on a subset of devices. And what we're able to do with QFFL is still perform roughly the same on average, but significantly improve the performance of these worst performing devices, potentially at the expense of some of these best performing devices. So what we're doing at a high level is we're reducing the variance of this accuracy distribution while maintaining roughly the same average performance. Okay, and you can see similar things for the real federated data sets that we looked at. So what's being shown in all of these plots is basically in the blue dotted line, you're seeing the accuracy, a density for the accuracy distribution for traditional ERM. And in red, you're seeing the distribution for QFFL. And so what you see for all of these at a high level, if you're just looking with a quick glance, is that the red distributions here are all kind of taller and sharper. So the variance is reducing. And as one kind of key takeaway from this work, we were able to maintain the average accuracy. So if the one statistic that you care about is kind of average performance, we're still getting the same average performance, but we're reducing the variance of this accuracy distribution. So we're helping to enforce more uniformity and to prevent against these catastrophic failures. So in working on this problem, we realized that this objective was actually useful for a lot of other problems in machine learning as well. So we looked at an extension of this, this prior framework, which we're calling tilted empirical risk minimization, or TERM. And the objective that you see is actually a slight reformulation of the QFFL objective. So this objective that I have here is a bit easier to reason about and to analyze. But the intuition is exactly the same as QFFL, except that in TERM, we also allow for one other kind of interesting variant, which is that in QFFL, the parameter Q, we allow it to vary between 0 and infinity, depending on whether you cared more about the average loss or this minimax variant. Here, we also allow T to be negative. And I think the reasoning for that is kind of best highlighted in a picture. So here's a picture kind of showing what the TERM framework would do for various values of T when solving a linear regression problem with outliers. So you can see here you have most of your data kind of lying along one axis, but then you also have some outlier points. Now, if we care a lot about these outlier points, if we want to enforce, say, fairness between all of the data, and we want to minimize the worst performing loss, or the, in this case, the largest distance between any one point and this regression line, then we can set T close to infinity, and we arrive at this red line here, which is kind of overfitting to these outlier points. Alternatively, if we think that those are outliers and we don't care about the issue, for example, of fairness, then we can ignore those data points by setting T to be a negative value. So for T going towards infinity, negative infinity. Okay, so here this blue line is kind of ignoring all of this outlier data. So there are a few nice interpretations of this framework. Depending on how you set T, you can think about it as reweighting samples to either magnify or suppress the effect of outliers in your data. And again, I'm using the term outlier here, but you could actually care about those outliers, right? They could be tail data points that you're trying to ensure that you incorporate to make sure that you have a fair model. You can think about tuning T as kind of enabling a trade-off between the average loss and the max loss or the min loss. And then one interesting interpretation of this framework as well is that you can view it as a smooth approximation of a super quantile method. So for example, if what you want to solve for is the median loss across your data, you can view a certain value of T as a smooth approximation to that objective that allows you to do something similar but more efficiently. Okay, so this is a little bit of an aside from federated learning, but I think the goal in showing this work was just to highlight that I think one nice thing about the space of federated learning in particular is that a lot of the ideas are quite general and can percolate into other areas of machine learning as well. And this is very recent work, and so if you're interested, you can check out the paper on arXiv. Okay, so going back to this question of fairness and equalizing performance across diverse networks, I think a few kind of key takeaways. One is that vanilla kind of ERM, if you're not careful, can deliver poor quality of service across heterogeneous networks. You might do well on average, but at the expense of some of the devices in particular. One thing that's nice about these frameworks, QFFL and TERM, is that they allow for a flexible trade-off between fairness and accuracy. I think moving forward, this is a really interesting and open direction in federated learning. So I think there's still a lot to be done to understand different notions of fairness and to understand the interactions between fairness and other objectives in the federated setting. So finally, I wanted to mention a little bit additionally about kind of going higher in the stack to the first problem in federated learning, which is kind of what model should you even select to fit to your data. And I'll be talking about some work that's fairly old at this point on federated multitask learning. But I wanted to bring this up because I think that some of the high-level ideas here are still very relevant to some of the questions that we have about how to best perform personalization in federated settings. So when we developed this work, kind of federated learning was just fresh on the scene. And one of the first things that we thought about in tackling federated learning is what is the best way to really model heterogeneous data? On one extreme, if you have a bunch of devices, you could learn a separate model for each of those devices. So you can learn completely local models. The obvious downside here is that while these models are very personalized, there could be some devices that have only a very few number of data points. And we want to be able to leverage some collective intelligence from all of the other devices to learn from our peers to hopefully deliver a better model to those devices. On the other extreme, though, if you learn a completely global model, you do a lot of sharing between your peers, but you don't necessarily have the benefit of personalization. And so the question that we asked ourselves is kind of what is in between these two extremes? And in particular, can we learn from our peers, but in a smart way, where we're learning only from kind of peers that are related to us in the network? So we're learning kind of what structure exists between this heterogeneous data. We want to allow for sharing information, but also enabling personalization. And I think the tension between these two extremes is really well captured via multitask learning. So in multitask learning, now you have separate models, one model for each device, for example, in the network. And each of these models you can stack into this matrix W. And then what multitask learning is doing is it's also enforcing this regularizer that basically tries to learn some structure between all of those models. And the way this structure is learned is via this task relationship matrix omega. So this is an old problem. There's been a lot of fantastic work on multitask learning in different settings, but I think it's particularly appropriate for federated learning because if you know information about your network a priori, you can put that information into this task relationship matrix in terms of figuring out kind of what components of the network are connected. However, if you don't know that information, one thing I really want to highlight about this framework is that you can learn it on the fly. So you don't need to know how to set this omega matrix beforehand. And the nice benefit of this is that you can both fit personalized models to your data, but you can also learn interesting relationships about the devices in your network. So for example, you can learn that all of the devices are related, but you can just learn the weights on the edges in this graph. Or you might learn that there are outliers in your network or that clusters or groups form between the different devices in the network. You can also learn interesting things like there is an asymmetrical relationship, for example, where there might be a power device or a power user that's generating most of the interesting information or content. And so this is a really, really general framework that can allow you not only to learn personalized models, but also to learn the structure between those models. And again, this work is from a little while ago, but when we applied this on some real, albeit small scale, federated data sets, the results are really clear, which is that multitask learning is able to do significantly better than just the global or just the local approaches. And one of the reasons is that it can go between these two extremes. So if you're in a scenario where you really care about personalization, you can handle that via this multitask learning framework. But if you're in a scenario where the global information is more important, you can also handle that. And on average, you can do much better than both of these because you can do this interesting thing in between of learning personalized models, but also sharing kind of the most relevant information between those models. So I don't have a great answer here in terms of how to make this kind of more usable and more scalable for federated settings. But I wanted to point out that multitask learning, especially if you're dealing with kind of a smaller federated network, is a really nice principled way to achieve these two goals of trying to learn something that's personalized, but also to share information between federated data sets. And I think there's been a lot of really nice work recently in thinking about related problems like transfer learning and meta learning in the federated setting. But I think maybe another way to approach the problem is to think about the way that we're instantiating multitask learning and seeing if there are ways to directly make that method more scalable for federated settings. Okay, so I wanted to end by just noting a couple things at a high level, a couple directions that I think are really critical for us to make improvements in this area of heterogeneous federated learning. And the first is that a lot of work currently is dealing with the issue of heterogeneity by sort of abstracting heterogeneity and then seeing how that abstracted version of heterogeneity might affect your optimization method or the fairness or the personalization of your model. And in particular, a lot of the approaches to measure heterogeneity deal with things like looking at the dissimilarity or gradient diversity across all of your data points, looking at the loss value across all of your data points, looking at this task relationship matrix in multitask learning. And all of these things are quite expensive to actually calculate in practice. And so I think a really important question moving forward is, are there ways that we can diagnose heterogeneity cheaply and ideally prior to actually performing training? And I think the ultimate goal here is to be able to deliver methods that can automatically diagnose and then adapt to varying levels of heterogeneity. Before we even get here, though, I think there's an even more important point, which is one thing that I think is really missing from the federated learning community is more access to real-world data and problems so that we can better understand what heterogeneity looks like. As one step in this direction, with a lot of great collaborators, we developed this benchmark called LEAF for learning in federated settings. And I know that the TensorFlow federated team has done also a really terrific job of open sourcing data and getting these evaluation frameworks running. But I think there's still more to do here. And in particular, in order to understand the magnitude of the effect of heterogeneity for federated learning, we really need access to more real federated data sets. This is something that I'm quite excited about. I think is very important for kind of moving the needle with this field. And so if you have someone who has access to federated data, you're using it in practice, or you would be open to open sourcing your data, please let me know. I'd be really happy and excited to collaborate along these lines. Okay, and before I finish, one last thing I wanted to note, kind of just a meta point, that I think a lot of the problems I talked about today are related to a similar kind of high-level trend in the machine learning community, which is that accuracy is not the only objective we care about. There are additional concerns like computation or communication or interpretability or usability. And I think a lot of the interesting work going on is really at the intersection of all of these challenges. And one community that's very near and dear to my heart that's been working on this problem is the machine learning and systems community. I'm currently on the conference board for MLSys, and I wanted to just note that if you're working in this space, submissions for MLSys are due on September 22nd. And you can find the more information and the call for papers on the MLSys website. And I think that federated learning is certainly a space that is really at the intersection of these two domains of machine learning and systems, and is trying to answer a lot of these interesting and important questions. So thanks, that's all I had, and I would be happy to answer questions.
Thanks a lot, Virginia. This is fantastic. In fact, we already have a few questions on Dory, so if you have questions, please post them on Dory, and I will share Dory to everybody so that we can go through the ones that are already there. All right, so let's do this. Hopefully everybody can see my screen now. All right. So first of all, I had a question myself, which is you talked a lot about fairness and how we can improve on this front, but you didn't mention the tension with privacy. I mean, you did mention it in passing, but what's your view on your techniques in terms of privacy? Like, can we improve on both fronts at the same time, or do we have to trade off one for the other?
Yeah, I think that's a really great question. I think this was brought up at the keynote yesterday as well. So I guess one issue I guess is just talking about this in the with the current definitions that we have access to of privacy. And I think there, it's clear that in order to make things private with traditional notions of differential privacy, you're going to be doing more masking of this of the tail data in order to make sure it's private. So I think there is something fundamental there with the current notions of privacy that's really at odds with delivering fairness. I would hope that there's some way to achieve both goals, and it may require kind of redefining some of the notions that we have of privacy in some way. But I think it's a really, really important problem to think about how fairness composes with these different issues of privacy and also robustness and efficiency and things like that.
Nice. All right, so let's take questions from our audience. Adam has a question. He says, regarding fairness and the tilted empirical risk, if there are multiple classifiers with similar overall performance but different performance on subpopulations, is there an opportunity to improve the overall performance through boosting or maybe specializing the model on different subpopulations?
Yeah, that's a really great point. So let me just go back to the term objective. So in this work, kind of the constraint that we had was the idea that we were learning a single global model, and we wanted to kind of reduce the variance of that model in terms of the accuracy distribution as much as possible. I think a really natural way to help with fairness is to use personalization for exactly this problem, which is that if you can indicate that there are certain parts of the network where there are these catastrophic failures, can you kind of switch and do something else for those settings? And yeah, maybe there's a way to do that in a boosting way that would be kind of interesting, or kind of in an iterative way where you solve kind of the global model and then you refine it. And I think, we've actually been looking at this a little bit with multitask learning as well. I think it's kind of intuitive given how much the accuracy improves with multitask learning. It also improves the variance of the accuracy distribution. So I think that's another one related to the last question, where looking at kind of the intersection of fairness and personalization would be a really useful path forward.
Thanks. Mehdi has another question. So he says, thanks for the nice talk. Have you explored other techniques from mathematical finance? Example, conditional value at risk, entropy VAR, mean variance, extreme value theory for this problem?
Yeah, that's a really, really great question. So I think one thing that's funny about this term objective is we came about it in a really roundabout way, which is that we were looking at this fair resource allocation problem in federated learning, and then we looked at this kind of extension and generalization, and we realized that this problem, even though it's not been looked at a lot for the problem of federated learning or even machine learning in general, it's been looked at a lot in different sub-areas. And that was kind of one thing that we hoped to highlight with this term work, which is not that we're proposing this entirely new objective, but that this objective and very similar objectives have been used in prior work. Like in finance, it's also been used, this conditional value at risk objective has been used in reinforcement learning previously as well. And we didn't look at value at risk in particular because the connection that we made in the work is that this is an approximation to that objective. And so I think that this could provide some of the same benefits as that objective, but is slightly easier to solve. And I think that high level, my answer to your question is, I think one really promising direction moving forward is taking some of these objectives that are used in other areas and thinking about them in the context of machine learning. So certainly I think there's more work to do in this area, especially with some of the objectives that you mentioned.
Cool. So John K has a question. He says, thanks a lot for the impressive work, super interesting. He wants to know, in QERM, in practice, how do we determine Q? And the same question applies for turn. How do you determine T?
Yeah, thank you for that question. Yeah, so in general, what we've done in this work is to show what the trends are, basically, both theoretically and empirically, as you tune Q or T in QFFL or in term. And the way that we're actually imagining this being used is that if what you care about is the fairness of your model, it might make sense to do this for a few values, to train a model for a few values of Q or a few values of T. And this is what we do in all of our experiments as well. We train it for a few values, and then we look at the performance on held out data. And that allows you to kind of see what the performance might look like, and to, as a practitioner, to make the final call on this trade-off between fairness and accuracy. Because I think this is ultimately something that it's not necessarily clear that we want to be able to automate this. I think this is something where we want to enable a practitioner to say, what are the things that they care about? And we want to make it as easy as possible for them to put those constraints in.
Thanks. So Mandy asks again, beyond ERM and TRM, learning invariance across environments seems to be neglected or overlooked. Leon Batu's IRM provides a very interesting trade-off where prediction takes a lower importance compared to invariance. Any thoughts on this?
Yeah, that's a good question. Funnily enough, we just some of my collaborators and I were just talking about this this work a couple of weeks ago. I don't have great thoughts right now. I do think it's a super interesting way to think about the problem. And yeah, in general, I think there might be a bunch of ways to try to achieve this trade-off. So this is the term objective, I think, is one that is nice just because we can characterize a lot of what the kind of direct results are in terms of these two notions of fairness or accuracy. But I think the general space is quite interesting. So yeah, thanks for the question.
Yeah, we'll take one last question. So Larita asks, in the federated learning setting, data can often be noisy. Tilting generally achieves only objective of either boosting outliers or suppressing noisy outliers. How would TRM help address the problem of fairness in the presence of noisy data?
Yeah, thank you. That's a great question. So actually, one thing that's kind of cool about this term objective is in the paper, we also define something that we call a hierarchical term. And I think it's nice in that what it allows you to do is to use different values of T for different kind of portions of your data set. So for example, if we're in the federated setting, if you have noisy data on your device, but you want to achieve fairness between devices, you can set one value of T locally to be negative to get rid of that outlier data. And then you can set a different value of T kind of at the more macro level across devices to help achieve fairness and help to deal with noisy data simultaneously. So that's one thing that is nice about the framework, is that it allows you to do both of those things simultaneously and to kind of optimize for both of them in a holistic way. The one caveat there is that you have to have this kind of hierarchy in place. So I think it makes a lot of sense in the federated setting, but in other settings, you would need to kind of know what those groups or hierarchies are that you care about for your problem.
All right, thanks so much. Please all join me in thanking Virginia for the amazing talk. Dory is open, so feel free to post questions. Virginia, please take a look at Dory, enter the questions you want to carry some discussions. For now, we're going to take a brief break, a 7-minute break. We're going to return at 10 a.m. So please stay on the call. You can mute, go, stretch, take a break. And next up, we have Google presentations in this room. Thanks, everybody.
Awesome. Thanks, everyone.